Lesson 10.1, Exponential Growth and Decay. This is a brand new formula for us, and it's our first unit on exponential growth. Just to kind of give you a heads up about what we're looking at here. Exponential growth, if we saw it on a graph, would look like this. Okay? Exponential growth starts out growing slowly, and then it starts to go very, 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 very quickly after that. So that's kind of an idea of what this function looks like, and we will look at that more tomorrow and the next day. Here is the formula of y equals a times b to the power of x. And now each of these things has a certain significance. So a, we refer to this as the initial amount. And something important to note is that this number cannot equal 0. All right, it's also our y-intercept, which is always going to occur at 0, and then that a value. Okay? The b value is super important. Your b value is your growth factor or your decay factor. So exponentials can be growing or they can be decaying, right? Increasing or decreasing. The way that we tell which is which, it's growing if b is greater than 1. So it's decaying if b is less than 1, but we don't really care about negatives, like we're not, I guess I should put absolute value here, right? We're ignoring the sign of b. If it's a fraction or a decimal less than 1, you're going to have decay, and if it's bigger than 1, you're going to have growth. All right, last but not least, okay, it's super important to note that b cannot equal 1. All right, and the reason that b cannot equal 1 is because if I used a 1 right here, no matter what exponent I use, I'm always going to have a 1. All right, so it would not allow us to grow. Let's look at the x. In this case, x is our exponent. It's the first time that we've had a variable as an exponent. And when we're looking at x, we are asking ourselves how many times. That's usually what we're using for that x value. All right. The next little part here is kind of an aside. We're looking at something that we haven't looked at in a while. We're looking at function notation. And we're doing this because it's good review and also because we're plugging in numbers for an exponent, which is new. So here's my function, f of x equals, I got -3 times 6, and then I have an exponent right up here. And that's where x is. Right now, x always matches what's in the parentheses. So in this case, I'm plugging in a -3. And all I do is plug that in my calculator. All right, so we're going to, in my calculator, we're going to plug in -3. We're going to use parentheses around the 6, and we're going to put to the power of -3. All right, now I want a fraction just so it's prettier, so math, enter, enter. And we've got -1/72. All right, the next two problems are very, very similar. You're doing the exact same thing, just with different exponents. We're going to do a -3, we're going to do a 6, but this time, for our exponent, I'm going to use a -2. Okay, and I'm going to do something cool in my calculator. If I press second enter, and then I do second enter again, it'll give me the one before that, and now I can just go in here, I can just change this number to a 2, and this is my new answer. Okay, let's do math, enter, enter again. And we have -1/12 for this answer. And then finally, same thing, kind of overkill here. We're going to use a 4 for my exponent, +4 this time, which is kind of new. All right, so second enter, and I'm just going to delete my previous exponent, and I'm going to use the number 4. And this gives me -3,088. 888. Okay. Now it's time to get into the actual meat and potatoes here of exponential growth, especially just looking at their tables. So we're really going to break this down into the basics here. Something very important to notice is look at how my y's are increasing. In order to get from 1 to 6, this is the first time we've seen it multiplying by 6, right? 6, to get from 6 to 36, we're going to be multiplying by 6, right? 6 to 216, we're multiplying by 6. Everything else we've done so far has either been adding by a constant rate or looking at the second differences where we've still been adding. So this time we're multiplying. Y'all, that's what makes this exponential, is we're multiplying from one term to the next. Okay, so my initial amount occurs when we have a 0 for an x value, right? Doesn't that make it the y-intercept? So my initial amount in this case is just 1, right? We might want to write this down. Occurs when x equals 0. My growth factor is just 6 because we're multiplying by 6 each time. I'm going to use x for my exponent, and so my equation, right, y equals ab to the x. A is my initial amount, so 1 goes in the front. My growth factor, b, is 6, and then to the power of x. Make sure your handwriting is good enough so that you can tell it's an exponent, right? It's smaller, it's also written up higher. Problem 2, here we go. This is the same stuff with one small difference, and that is, take a look at my table. What's missing? Sorry. What's missing? All right, maybe you don't see it yet. Let's move on. How do I get from 9 to 81? Okay, hopefully we know that's times 9. How do I get from 81 to 729? Again, that's times 9, times 9, and then finally times 9. So my growth factor is 9. But what is my initial amount? Don't tell me 9. It's not 9, right? Remember, my initial amount occurs when x is 0. So my initial amount, we're going to have to figure out what goes there. What happens when we get a 0? What happens when x is 0? So we can think of this a couple of ways. What times 9 is 9, right? What times 9 is 9? Okay, well, that's just got to be a 1, right? 1 times 9 will give me 9. Another way we can think about it is, what if we move up the table? If we look at it like this, then we can think of that as dividing, right? Divide by 9, 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 and we end up with that 1. So just as long as you understand the relationship in the table, you should be able to figure out a number right above or even right below. So my initial amount is 1. By the way, it's just a coincidence that I got 1s for both of those initial amounts. It does not always have to be 1, which we will see in just a second. My exponent is still just x, so to write this equation, I'm not going to write the formula again. We should just have y equals 1, my initial amount, times 9, my growth factor, to the power of x. Okay, finally we have a word problem here. A rabbit population doubles every year. If there are 2 rabbits to start with, how many rabbits will there be in 5 years? So let's break this down into my equation. What is A? Well, A is my initial amount. So that's got to be 2, right? 2 rabbits to start with. That's my initial amount. Now what is B? Remember, B is my growth factor. Well, in this case, we're doubling every year. So B has got to be 2, right, for doubling. And X is my how many times, right? So 5 years. So here we're going to write y equals 2 times 2, right? There's my formula. And I want to know after 5 years, so we're going to use 5 for an exponent. So type it in your calculator just like that, or use order of operations to find out that 2 times 2 to the power of 5 is 64. All right, so 64 rabbits. All right, on the back side of this paper, right on the next part, we're no longer looking at exponential growth, we're looking at exponential decay. And I think you probably can notice that that's what's happening, right? The numbers in my table this time are going down. But going down how fast? By what rate are they decreasing? I actually am not really familiar with these numbers, so I'm just going to choose the first 2. And I'm going to find out what is 6561 divided by 2187. All right, because this will tell me how much I am dividing by, so I can really see kind of what's going on. So 6561 divided by 2187, and I get 3. All right, so it looks like we're dividing by 3 each time. All right, dividing by 3, but my growth factor is not 3. Remember, we said if it's going to be decay, it needs to be between 0 and 1. Also, we have to be multiplying. So like I know that it looks like we're dividing here, but we have to do this as a multiplication statement. So dividing by 3 is the same as what? Same as multiplying by 1 over 3. right? Let me just demonstrate for you. If I, let me look at the 243 and the 81. If I do 243 divided by 3, obviously I get the 81, right? But if I do 243 times 1 over 3, then I still get 81, right? I get times 1 over 3, and it still produces 81. So dividing by 3 and multiplying by 1/3 are the same thing. So my decay factor, I have to use 1 over 3. All right, whatever this is, you can put a 1 over it to make it a multiplication problem instead of a division problem, right? It's the reciprocal. Now my initial amount is still pretty simple, right? I have 0 in the table, so my initial amount is 6561. 6561, so my equation with x as my exponent is just y equals 6561, my initial amount, my growth factor is 1/3 to the power of x. All right, next example. So again, we can see that we're decreasing, right? We're decreasing. And I know 49 and 7, I know 49 divided by 7 is 7. So instead of writing out a bunch of times divided by 7, let's write it as a multiplication statement. What is the same as dividing by 7? Multiplying by 1 over 7. All right, guys, we're multiplying here. We always need to be thinking about it in terms of multiplication instead of division. So that's my growth factor, my decay factor, 1 over 7. Now what is my initial amount? Okay, it's not this because I need x to be 0. So what is my initial amount? Well, we're going to just kind of have to use our brain here. My initial amount needs to be when x is 0. It's going to be bigger than this because it's going to go in this spot in the table, right? I think a nice way to do this is to kind of work backwards, right? If I'm dividing by 7 each time, all right, multiplying by 1/7, what if I go backwards? Isn't this times 7, times 7? Times 7, times 7, times 7, times 7. So we're going to multiply by 7 to find that bigger number that we're missing. All right, we're going to do, let's see here, 16807 times 7 to get 117649. So 117649. That is my initial amount. All right, my exponent is still just x. And so my equation is going to be y equals, my initial amount goes in the front, that's this huge number. My decay factor goes in the parentheses, and we have to the power of x. Okay, last thing we're going to look at here is just a word problem, right? A word problem with decay. So a scientist has 20 bacteria. With the use of antibiotics, half of them die every 5 hours. How many are there after 15 hours? Well, let's see. We got y equals AB to the x. My initial amount is going to be 20, right? 20 bacteria. What's my decay factor? Okay, it's going to be half. I'm losing half of them. That's the rate at which they are decaying. So 1/2. So my equation is y equals 20 to the power of times 1/2 to the power of x. Now, if half of them die every 5 hours, and I'm looking for how many are there after 15 hours. Okay, well, think about this. 15 hours is going to be 5 plus 5 plus 5 hours. So x is equal to 3. All right, we have 1, 2, 3 cycles of 5 hours. So we can only use 3 as our x to find this number. All right, what do we get? We need 0.5 to the power of 3. All right, so we are getting 2.5. So I'm going to say about 3 bacteria, right? I'm assuming we can only do whole numbers when we're talking about these bacteria. All right, that's your brief overview on exponential growth and decay. Just remember, growth factors, b is greater than 1. Decay, you need to have a fraction in there, right? A number between 0 and 1.